Hello everyone, welcome back. In this particular video, we're going to start talking about carboxylic acid anhydrides, which are also simply called acid anhydrides or just anhydrides. This video will focus on the preparation and reactions of anhydrides. Now, in terms of preparation, one of the simplest preparations for acid anhydrides that you can imagine is from carboxylic acids. You can just dehydrate a carboxylic acid to get an anhydride. So if you have a carboxylic acid, and to be specific, you need two equivalents of this carboxylic acid. So you can take two equivalents of a carboxylic acid and then dehydrate, which means the loss of water. So you're losing water overall in this reaction. So you can show it here, but notice how I've shown it on the other side, on the product side. So it is a dehydration when you lose water, and it would give you the anhydride. Now, this process is usually done at high temperatures, several hundred degrees Celsius high temperatures. So this is not practical for all carboxylic acids, because once you get like carboxylic acids with longer carbon chains, it would participate in like other decomposition reactions. But this is very practical for making acetic anhydride. So if you look at it, what we have here is acetic acid, which is the 2-carbon carboxylic acid, and you can convert it into acetic anhydride using this process. So carboxylic acid anhydrides can be synthesized from the carboxylic acid or can be prepared from the carboxylic acid via a dehydration reaction. Now, a more practical approach for making a wide variety of acid anhydrides is using an acid chloride and a carboxylate ion. I'll add the detail here. So it's a carboxylate ion, specifically it's an anion. Now, a carboxylate is this molecule. Okay, that's the carboxylate. Now, if you think about it, this carboxylate is actually the conjugate base of a carboxylic acid, because if you remove a proton from a carboxylic acid, that would give you the carboxylate ion. So using a base, okay, so that's the carboxylic acid. So in some sense, this is again a synthesis of anhydrides starting from a carboxylic acid, okay? But what we actually need is the carboxylate ion. So if you take a carboxylic acid and you treat it with a base, react it with a base, you will get the carboxylate ion, which is the conjugate base of this carboxylic acid. And now the carboxylate ion can be reacted with an acid chloride to give you an anhydride with the loss of a chloride. Now, overall in this process, we're losing a proton here, we're losing a chloride over there, so you're losing HCl, but we also have the base, which is taking care of that acid that's produced. Okay. Now, the mechanism of this reaction is a nucleophilic acyl substitution, follows the same mechanism as any other nucleophilic acyl substitution. So essentially what happens here is, you have the acid chloride, which is a great electrophile. It is the most reactive of carboxylic acid derivatives. The carboxylate ion does a nucleophilic attack on the acid chloride at the acyl carbon. That would push up the carbon-oxygen double bond towards the oxygen. And this is going to give us an intermediate where we have double bond O. This oxygen has 2 lone pairs, and we will have oxygen with a minus on it. There's an R group over here, and there is a chlorine on that carbon. So that was the acyl carbon, and this R is an R prime. We're trying to differentiate it from the other R group. So you get the tetrahedral intermediate, and when the tetrahedral intermediate collapses, the chloride is going to leave, and this would essentially bring you to the anhydride. Okay, so through the formation of a tetrahedral intermediate and the collapse of the tetrahedral intermediate, you would get the anhydride plus the chloride ion. Now, this method is suitable for making both symmetric and unsymmetric anhydrides. Okay, so can be used to make symmetric or unsymmetrical anhydrides. And what we mean by that is that when you're doing this reaction, the identity of the R group and the R prime group, that could be the same, it could be identical, or it could be different. So if both R and R prime are the same group, then we will get a symmetric anhydride because R and R prime are the same. But if R and R prime are two different carbon-containing groups, then we get an unsymmetrical anhydride. Okay, so those are the reactions that help us to prepare acid anhydrides. Next, we are going to look at the reactions of anhydrides. Now, anhydrides, being carboxylic acid derivatives, they undergo the nucleophilic acyl substitution. And their reactivity, or the pattern in which they react, is very similar to acid chlorides, which we've already looked at in a previous video. And when you compare the structure of an acid chloride to the anhydride, or an anhydride to an acid chloride, what you should recognize is that in an acid chloride, this chloride group is the leaving group, and we keep the acyl group. That's where the reaction happens. So when you come to an anhydride, now a carboxylate group, that's your leaving group, and we still keep the acyl group. So in some sense, when you compare an anhydride to an acid chloride, you notice that a bigger chunk of the molecule is behaving as a leaving group compared to the acid chloride, where it was just the chlorine. So it's a much bigger part of the molecule that behaves as a leaving group. But irrespective, the reactions and the reactivity is kind of similar to the acid chlorides, but acid chlorides are more reactive than anhydrides, so they're more reactive. Okay, so if you look at the reactions, and we'll start with the hydration or the hydrolysis again. Anhydrides can react with water, and this is a hydrolysis of the anhydride. And what this reaction does is it would convert the anhydride into carboxylic acid. Okay, in fact, it would be more than one. There would be two carboxylic acid molecules that are generated. So if you look at the hydrolysis of a symmetric anhydride, let's say, this is going to give us two molecules of the same carboxylic acid. However, if we start with an unsymmetric anhydride, so let's say if we had an anhydride with two different R groups, and you do a hydrolysis of this unsymmetric anhydride, you're going to get two different carboxylic acids. You're going to get a carboxylic acid that corresponds to the R group, and another carboxylic acid that corresponds to the R prime group. Now, anhydrides, they're still pretty reactive as far as carboxylic acid derivatives are concerned. So when you have anhydrides stored for a long time, they can slowly hydrolyze using moisture from the ambient air. Okay, moisture is basically water, so it can react with the anhydride and can slowly cause a hydrolysis of the carboxylic acid anhydride to the carboxylic acid. Let's look at a specific example here. So if we consider maybe an anhydride where we have that, it's a methyl tert-butyl anhydride. Okay, there's a methyl group on one side, there's a tert-butyl group on the anhydride. So if we react this with water, it is going to give us acetic acid plus the carboxylic acid with a third butyl group on it. Okay, it's going to give us two carboxylic acids like that. Now, the mechanism of this reaction, again, it's very similar to other nucleophilic acyl substitution reactions, and we can work on a mechanism here. And I chose this example of an unsymmetric anhydride to basically put across a point. So when you have carboxylic acid anhydrides like unsymmetrical ones, notice you have two electrophilic carbons here, two acyl carbons. Okay, this acyl carbon is electrophilic, and this is also an acyl carbon. So they are both acyl carbons. So that raises an important question. Where would the water attack? Okay, and as you can see, in terms of their electronics, they're pretty similar. So what this the position of this attack is going to be guided by the sterics or the steric hindrance around that electrophilic site. And as you can see, the second electrophilic site over here has a third butyl group next to it, which is a bigger carbon-containing group. Whereas on the first electrophilic site, there's only a methyl group. And so because of steric reasons, in this particular case, the nucleophilic attack is going to happen on this first acyl carbon because that's the less sterically hindered carboxylic acyl carbon. Now, this issue would arise only when you're dealing with unsymmetric anhydrides. If you're dealing with a symmetric anhydride like this, where both R groups are identical, you can attack pretty much either one of those groups because they are the same size. So it really doesn't matter. But in a situation like this, the attack happens on the less substituted acyl carbon, okay? And the double bond is going to open up. Or the less sterically hindered, sorry, not less substituted, but the less sterically hindered acyl carbon, and the double bond opens up. This would give us an intermediate where we would have the carbon, the acyl oxygen has a negative charge now. We're going to have O, C double bond O, third butyl. And on this carbon, we have the water molecule connected. And this oxygen has a positive formal charge on it. And after the attack, as with other nucleophilic acyl substitution reactions, the next step is going to be the collapse of the tetrahedral intermediate. That double bond comes down. And as it comes down, our leaving group is the carboxylate on the other end. So this carbon-oxygen bond is going to open up, and you're going to break that bond such that this will give us a protonated carboxylic acid, where that acid oxygen is protonated, okay, and plus it will give us a carboxylate. It will give us the carboxylate. So that's the leaving group. And so in the final step here, this carboxylate can deprotonate this carboxylic acid to give us our product. So that's the mechanism of hydrolysis. So since we are operating under sort of nucleophilic conditions here, there is no acid here, although you have the carboxylic acid as the product, but you're going to treat this as a neutral condition. So the first step is the attack of the nucleophile on the acyl carbon, formation of the tetrahedral intermediate, collapse of the tetrahedral intermediate, and then a final deprotonation to give us the product. And the key thing to remember here, as I mentioned here, is that the nucleophilic attack occurs at the less hindered acyl carbon if it is an unsymmetric anhydride. So that's the hydrolysis of anhydrides. Now let's look at the alcoholysis of anhydrides. Now this is the reaction of anhydrides with alcohols, and it's called the alcoholysis reaction. What it does is it converts the anhydride into an ester. That's the product, the organic product that we're looking at. Although there would be another organic product. Okay, we'll see that. So as a generalized reaction, you can treat this as the reaction between an anhydride reacts with an alcohol. Notice I'm using a symmetrical anhydride, both R groups, but it could be unsymmetrical. And we have an alcohol here. So this R prime is some carbon containing group that makes it the alcohol. And so what you get in the end is the ester. So you start with an anhydride and your product here is an ester molecule. This is an anhydride and it gives you an ester. And as we saw earlier, and whenever the anhydride is used as your carboxylic acid derivative, you're always going to make a carboxylic acid molecule, a molecule of carboxylic acid as your side product. So there's your organic product, organic side product is a carboxylic acid molecule. Okay, let's look at a specific example here. Here we have propionic anhydride. So this is a propionic anhydride because notice it is a symmetrical anhydride with 3 carbons in that acid. So it is propionic anhydride. You react propionic anhydride with an alcohol. So now the R prime here is the cyclohexyl group. So the product is an ester where we've kept the acyl carbon on one side and the rest of it is basically a leaving group. So you want to keep that in mind. The carboxylate here is lost at the leaving group. That becomes your carboxylic acid. And the acyl carbon here is directly connected to that alcohol oxygen. That's how you get your product. Now, the synthesis of an ester from an anhydride is a practically very useful reaction synthetically. In fact, this reaction is made for synthesizing aspirin. Okay, so aspirin can be synthesized using the using this anhydride chemistry because you start with an alcohol. Now this alcohol here is slightly more complicated, but this is the alcohol that you use, which is called salicylic acid. Okay, this is salicylic acid. And notice there is a hydroxyl group in it, and there's also a carboxylic acid group in the molecule. Now, the alcohol group or the hydroxyl oxygen here is more nucleophilic in this particular case. Okay, so when you take this salicylic acid and you react it with an anhydride, and it is a specific anhydride, which is acetic anhydride. Okay, the nucleophile here is going to go and attack that carbon. And again, remember for anhydrides, the carboxylate is your leaving group. So that's leaving. And so essentially what this gives us is aspirin with the, it's an acetyl salicylic acid, and that molecule is called aspirin, is sold under the trade name of aspirin. So I'm going to get that. That's our ester. This is acetyl salicylic acid. That's the ester, and plus the carboxylate leaving group here, that's going to show up as a carboxylic acid. So that would be the side product. So take note of that. In all of these reactions, in fact, every reaction of anhydrides, you're going to generate a carboxylic acid molecule as a side product that comes from your leaving group. Okay, the carboxylate leaving group becomes a carboxylic acid in your product. Next, we're going to look at the reaction of anhydrides with amines. Now, these reactions can generally be called aminolysis reactions. And what they do is they convert anhydrides into amides. Now, if you look at the scheme over here, I've sort of captured all possible scenarios, and the nature of the product depends on the nature of the reagent that you use, okay, the nature of the amine that's used for the reaction. So when an anhydride reacts with ammonia as your amine, then your product is a primary amide. And along with that, you're going to make some ammonium carboxylate as your byproduct. Okay, so ammonia gives you primary amide. If your amine reagent that you're using is a primary amine, then the product is a secondary amide along with some ammonium carboxylate byproduct. Now, the nature of this ammonium would depend on the amine that you're using, because that is what becomes the ammonium ion over there. And similarly, when you react your anhydride with a secondary amine, if your reagent is a secondary amine, then the product is a tertiary amide along with some ammonium carboxylate as your byproduct. So notice the nature of the product, whether it is primary, secondary, or tertiary amide, depends on the nature of the amine reagent. Ammonia gives you the primary amide, primary amines give you secondary amide, and secondary amines give you tertiary amides as products. Let's look at the mechanism of this reaction quickly as to how do we get this ammonium acetate byproduct. And we'll use the example of ammonia here. So when you have an anhydride and this reacts with ammonia, as we've discussed before, ammonia is a great nucleophile. So the first step here is going to be the attack by the nucleophile on the acyl carbon. And this would result in the formation of the tetrahedral intermediate. So we will get the tetrahedral intermediate from this first step. And we'll have the NH3 plus. Okay, that's the tetrahedral intermediate. The second step should be the collapse of the tetrahedral intermediate. And as the collapse happens, the carboxylate is lost. That's the leaving group. The carboxylate is lost. And this would give you RC double bond O with a nitrogen and 3 hydrogens. That's the ammonium. So you get the protonated amide along with carboxylate ion. Now, in principle, yes, you can use this carboxylate to deprotonate, but often the amine is used in excess. And so what happens here is, and it is a better base here, the amine is a better base. So what happens here is, after the formation of this protonated amide, another molecule of ammonia goes and deprotonates it, puts the electrons on the nitrogen, and so that would give us RC double bond O NH2, which is our primary amide product, along with some ammonium ion. And if you notice, we had a carboxylate and we had ammonium, so that's what makes your byproduct here. Okay, so that's the mechanism of this reaction. The reaction of anhydrides with amines is also a practically very useful reaction. For example, it's used in the synthesis of Tylenol. Okay, so we can look at that example here. So Tylenol is synthesized using this reaction. Or Tylenol has an amide as a functional group in it. So Tylenol is synthesized by reacting para-aminophenol, which is this molecule. Okay, it is a molecule which has both an amine and amine and a hydroxyl group in it. And in this particular case, the amine is a much stronger nucleophile compared to the oxygen here. So when the amine reacts with anhydride, and specifically acetic anhydride, okay, acetic anhydride is the same anhydride that we used for making aspirin when we were reacting anhydrides with alcohols. So the alcohol reacted with the anhydride, but in this particular case, the amine is going to react with the anhydride. And so our product here is going to be an amide, which is this. So it's basically an amide of para-aminophenol, and this molecule is what is sold under the brand name of Tylenol. Okay, so again, a very practical reaction. Again, this is just one of the many applications or many practical applications of this anhydride chemistry, where the anhydride reacts with amines. But these reactions of carboxylic acid anhydrides and the acid chlorides that we've been learning, these are very practical as far as day-to-day products are concerned. Next, we're going to look at the reaction of anhydrides with hydrolytic reagents, especially aluminum-based hydrolytic reagents like lithium aluminum hydride. So when anhydrides react with hydride reagents like lithium aluminum hydrides, they're converted into primary alcohols. So a general scheme is given here, where you have an anhydride, you react it with excess lithium aluminum hydride, and you do an acidic workup on it, and it gives you alcohol in the end. Now, what happens in this reaction is that the acyl carbon becomes the alpha carbon of your alcohol. And notice, very similar to acid chlorides, the alcohol that you get here is going to be a primary alcohol. That is what you get as your product. Okay. Now, the mechanism of this reaction is very similar to what we've seen with the acid chloride. So for a mechanism, we can say that it starts with the reaction of the anhydride with the aluminum hydride. Okay, so the aluminum hydride, and I'm skipping the lithium part here because the aluminum hydride part of it is what actually reacts. That's the source of the hydride. And so in this particular case, the hydride is going to come and do a nucleophilic attack at one of these acyl carbons if it is a symmetric anhydride. If it is an unsymmetric anhydride, again, the attack here would be guided by sterics. The less hindered acyl carbon would be attacked under these conditions. And so as the attack happens, the double bond opens up, and so it will give us the tetrahedral intermediate, where the hydride or the hydrogen is now connected to that acyl carbon. So we get the tetrahedral intermediate. Along with this, there will be the aluminum species. Now, as the tetrahedral intermediate collapses, this should result in the loss of the carboxylate ion. And it would give us an aldehyde plus the carboxylate ion. And again, this aldehyde can react with another molecule of aluminum hydride, with another hydride, because that's a carbonyl compound. So again, a lot of resemblance, similarity with what we saw in case of acid chlorides. And so that will give us the alkoxide here, plus the aluminum And then when you do the workup, which is the second step, under acidic conditions, the alkoxide gets protonated to give you the alcohol. And so the acyl carbon here, that becomes the primary that becomes the alpha carbon of the primary alcohol. Now, under this mechanism, notice that I've only tracked one of the acyl groups. The other acyl group came out as a carboxylate. So when we do this workup, okay, that carboxylate could get protonated and give you a carboxylic acid. But the other possibility is we are operating under excess aluminum hydride, lithium aluminum hydride here. So if there is enough hydride available, realize that or recollect that a carboxylate can be reduced by lithium aluminum hydride to give you the same alcohol. So with an excess of lithium aluminum hydride, both the acyl carbon here and the carboxylate that's generated, that could be reduced to the alcohol here. So overall, your product is going to be an alcohol from the reduction of anhydrides using lithium aluminum hydride. Next is the reaction of anhydrides with organometallic reagents. We'll look at a specific example here where we are looking at the reaction of anhydrides with Grignard reagents. So very similar to acid chlorides, when an anhydride reacts with an excess of the Grignard reagent, it is converted into a tertiary alcohol. Okay, so an anhydride with excess Grignard reagent followed by acidic workup gives you a tertiary alcohol where two molecules of this Grignard attack that acyl carbon one after the other. So the mechanism, again, I'm not going into the details here, but it's very similar to the reaction with the acid chlorides. The initial attack by the Grignard gives you a ketone, and the second attack of the Grignard on the ketone gives you the tertiary alcohol. I've basically put down an example over here where we're looking at the reaction of an acetic anhydride with ethyl magnesium bromide. And under these conditions, you get the tertiary alcohol where two ethyl groups have added to one of these acyl carbons. Okay, so if you look at the carbon, there are two ethyl groups that have added, and you've got acetic acid. So the leaving group that came out as a carboxylic acid. So the alpha carbon has two of these R groups added from the Grignard reagent. So those are all the reactions of anhydrides that we'll be covering here. Now notice there is a lot of similarity with the reaction of acid chlorides. And these are the second most reactive carboxylic acid derivatives. Acid chlorides are the most reactive, and anhydrides are the next set of reactive carboxylic acid derivatives. So I hope you find this video useful. Refer to the video of the acid chloride chemistry in case you have any doubts. Bye.